Okay, so this is the notes for 5.8 part 2. Now we're going to talk about decay. So the amount A of a radioactive material present at time t is given by, now it's the same formula, A sub 0 e to the kt, but this time our k is negative, so that's what makes it a decay problem, where A sub 0 is the initial amount and k is a negative number that represents the rate of decay. Okay, there's a note, all radioactive substances have a specific half-life, which is the time required for half of the radioactive substance to decay. That's what half-life means. And I'm actually going to give you a different formula for half-life. Okay, so let's do a decay problem. I think you'll see it's very similar to what we were doing with the rate of growth problems. Okay, so iodine-131 is a radioactive material that decays according to this function. Notice that my K is negative, where A sub 0 is the initial amount, A is the amount present in time in days. Assume that the scientist initially has a sample of 200, so that means that's A sub 0. Let's decide what some of these are. What is the decay rate? Well, remember, that's our K. It's 0.087. So that means that our decay rate is 8.7% per day. It's decaying at that rate. How much of that substance is left after 5 days? We're just looking for A sub 5. So you would simply plug in 200 for A sub 0, E to the negative 0.087 times 5. And I did the math. You should get about 129 grams, which makes sense. We started off with 200 grams, don't forget. When will the 100 gram, or when will there be 100 grams left? So that 100 is my A sub t, so that's 100 is equal to 200 e to the negative 0.087 t. Let's divide by 100, or 200, so that's going to be 0.5 equals e to the negative 0.087 t. Natural log both sides. So we're going to get the natural log of 0.5 equals negative 0.087 t. And when you divide both sides by that negative 0.087, I got 7.97, which to me is good enough to round off to 8 days. So after 8 days, there'll be half of that left. So by the way, what that means is that 8 days is your half-life. All right, well, let's look at this now. So upstairs, up at the top here, they kind of have a fact. So if you would just take a second and you can read that. It's an interesting fact. They talk about the fact that carbon-14 is said to have a half-life of 5,730 years. So we're actually going to use that in example 4. Okay, so now we have to find the equations for decay. So here's the deal. I'm going to show you a half-life formula that will always work whenever you're talking about a half-life problem. And it makes the job a little bit easier than having to have it as a 2-step problem. So here's the half-life formula. In this case, it's going to be A sub t is equal to A sub 0. And now your base is going to be 1/2. It's always 1/2 for a half-life problem. And then you're going to have T over H, where H is the years in a half-life. So in this case, our H is going to be 5,730. Now watch how this works then. So if we read the problem, it says traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? So we're looking for time. So here's what we're going to do. We know that after a certain amount of time, there's 1.67% left. So we're going to use 1.67 as our A of t. That's the amount left. Well, how much is left at the very beginning? What percent? Our A sub 0 is going to be 100% because it started off as 100%, and we want to know how long will it take down to get down to 1.67%. To the, I'm going to use 0.5 for 1/2 just because it's easier in the calculator. And then to the t over 5,730 years. And as you can see, we're simply looking for t. So let's do the math. If I divide both sides by 100, I'm going to get 0.0167 equals 0.5 to the t over 5,730 power. Now we don't have an e, so we're not going to use natural logs. I'm going to take the common log of both sides. Now I'm going to take this exponent and bring it down in front. So it would be, let's see, log of 0.0167 is equal to t over 5,730 times the log of 0.5. Let's divide by the log of 0.5. So if I take that and divide it, actually I haven't done that, so let me quick do that. So that would be the log of 0.0167 divided by the log of 0.5. Sorry about this. And I get about 5. I'm going to go 5.9 is equal to t over 5,730. And then simply to find t, you'll take that 5.9 and we're going to multiply it by 5,730. And we get about 33,800, I think it's years. Okay. So what that means is that that tree was actually cut down almost 34,000 years ago. That's a long time. All right, let's get through Newton's law of cooling. So this is an interesting formula, and we're going to use the grapher too. So if we go ahead, it says the temperature U of a heated object at a given time can be modeled by the following function. So here's the function. U of t is equal to capital T plus U sub, oops, that should be a U, my apologies. U sub 0 minus t times e to the kt power, where k is less than 0, so k is going to be a negative constant, where T is the constant temperature of the surrounding medium, U sub 0 is the initial temperature of the heated object, and K is a negative constant. So basically this is going to tell us, okay, if we cook something, how quickly does it cool down? That's really what we're looking for. So let's kind of look at this example. It says an object is heated to 75 degrees Celsius and is then allowed to cool in a room whose air temperature is 30 degrees Celsius. If the temperature of the object is 60 degrees after 5 minutes, when will the temperature be 50 degrees? So now this is going to be a two-part problem. In fact, I'm going to go ahead and I'm going to draw a line right there, because the first thing that we're going to have to do is we're going to have to find K. We don't know K. And then we're going to plug K in and use that equation to find the answer to that question. So we're going to use the formula from up there. So it says if the temperature of the object is 60 degrees after 5 minutes, those are the two numbers that we're going to use to help us find our K. So we're going to plug 60 in for U sub t, and t is going to be 5, is equal to 30. My initial temperature is 30 because that's the room temperature, plus 75 minus 30. 75 is the temperature that it was heated to originally, and then minus 30, e to the 5t. And again, it happens after 5 minutes. So it cools till 60 degrees after 5 minutes. It starts at 75, and the temperature of the room is 30. So let's quickly go ahead and solve this. So if I subtract 30, and if I subtract there, I'm going to get 45. So that's just simplifying a little bit. If I divide both sides by 45, I'm going to get its 2/3. So I'm going to put a bunch of 6s and a 7. I don't want to round too much. Is equal to e to the 5k. Take the natural log of both sides. So we get 5k is equal to the natural log of 0.66667. And if you divide that natural log by 5, you're going to see that you get approximately negative 0.0811. So that is my K. That is how fast this object is cooling. It's at 8.1%. So now let's rewrite our formula with our K in it. So we have the initial, or the room air temperature of 30, plus U sub 0 minus 30, e to the negative 0.0811 times t. So there's our new formula. Now it says, when will its temperature be 50 degrees? So we're going to plug 50 in for U of t. This is still going to be 75. Aren't you glad you can pause this at any time to catch up? So we would get 20 equals 45 e to the negative 0.0811 t. Divide, we get 0.444 equals e to the negative 0.0811 t. I'm not going to show the next steps because I did it already over here. You should be able to do it. I will tell you that you get t is about 10 minutes though. So it'll take 10 minutes for it to get down to 50 degrees. So now look, it says using a graphing utility, graph the relation found between the temperature and the time. So I've already put this in my graph, and I do want you to see that. So I've put the original equation in there. So it's 30 plus 45, because that's the 75 minus 30, e to the negative 0.0811x. And I'm going to tell you that I used a window. Well, let's see, I'm going to use x min of 0. I'm going to use x max of 50. Oops, sorry about that. Let's delete that. I'm going to use an x max of, we'll do 54, a y minimum of 0, and a y maximum of 80. So that's my window. And when I go and I graph it, you can see that. So that is your equation that we plugged in. So now, what does it want us to do with that equation? Well, it says using the grapher, verify the results, so we could do that. Determine the elapsed time before the object is 35 degrees. So we want to know what is my x when my y is 35. So if you go and if you press trace, and if you trace the graph, you're looking for when is y 35. Well, it's really close to 35 right there. So what is my x, or my time, when the y is 35 degrees, or when it hits 35 degrees? You can see that my x is about 27 minutes. So after 27 minutes, that 75 degree object will be down to 35 degrees. Then just last, it says, what do you notice about the temperature as time passes? Well, if you keep tracing this, what's going to happen is you're going to see that the temperature is going to get closer and closer to 30, which should make sense. What it happens is it approaches that room temperature. All right, I'm going to stop this and go on then to